Okay, so these are our final two titration type problems I want to look at, and I hope you guys are watching this video. You are going to be held accountable for some of this, so hopefully it'll be clear, and if you have questions about them, you can come and talk to me. But looking at this one, we have an obvious titration curve on our picture, and the first problem is saying a 30 ml sample of a weak monoprotic acid. Weak monoprotic meaning it's not going to dissociate much, and it is a 1H acid. Was titrated with a standardized solution of NaOH. What does standardized mean? That's a really important thing in order to make this problem successful. To be standardized, it means that we know the molarity of that sodium hydroxide solution. A pH meter was used to measure the pH after each increment of NaOH was added, and the curve above was constructed. So part A says, explain how this curve could be used to determine the molarity of the acid. Since we don't have a lot of data here, they're not specifically asking us for the calculations to do this. They want us to verbally describe how we would do it. So the first step we're going to do is locate the equivalence point on the curve, which is going to be somewhere in the middle of the sharp rise. So that's my first step. Find the equivalence point. And then what we need to do is determine the number of mils that we titrated of sodium hydroxide to get to that equivalence point. All right, once we know that, we can then, because this is a standardized solution, multiply the volume of NaOH. We just talked about the volume of NaOH to get to the equivalence point in liters times the known molarity. And when we multiply volume times molarity, we get moles. So we do that to get moles of NaOH. Definition of equivalence point is that the mole at the equivalence point, the moles of the base is equal to the moles of the acid, especially in this situation where it's a monoprotic acid. So hey, knowing the moles of NaOH, we then know the moles of H+. So how do we figure out then the concentration of the acid? We take the moles of H+ and divide it by the volume of the acid, which was in our little Erlenmeyer, and they gave that volume to us specifically as 30 mils or 0.0312. Yeah, 0.03 liters. And that will give us our concentration. Okay? So that's how we use the curve to find that. So part B then asks, explain how this curve could be used to determine the Ka. I don't know if you remember when we were talking about these kind of curves yesterday or this morning, depending upon when you had the lecture, there was something called the half equivalence point. Find the half equivalence point. So what the half equivalence point is on this chart is, you know where your equivalence point is. Half equivalence point is halfway to that. So if this is about 24 mils, the half equivalence point would be here. At the half equivalence point, and I'm going to go ahead and write this down for you because we already talked about this a ton. At the half equivalence point, what we've done, we've taken and neutralized half of our HA, our acid, and it became the same amount of A-. So the A- concentration is equal to the HA concentration at the half equivalence point, and we've seen this a bunch of times in thinking about Henderson-Hasselbalch. If those two things in the buffer, in that buffering region of the curve are the same, we then know that at that point the pH is equal to the pKa. So that's all we really need, is to find the pH at the half equivalence point. So if the equivalence point, and again you can look back up at the graph, is approximately 24 mils, we know the half is approximately 12. The pH at the half equivalence point is about 5. So if that's the pH, we then know that the pKa of the acid would be 1 times 10 to the negative fifth. Not the pKa, excuse me. The pH is equal to the pKa. So then the Ka would be that. We know that the pH is equal to the pKa, which is equal to 5. So if I go 10 to the negative, that's where I get Ka. So the Ka is basically the inverse log of the pH at the half equivalence point. So learn that term. Some people call it the halfway point as well. Either one's acceptable. All right, Part C. Part C says, if you were to repeat this titration using an indicator, instead of making a curve, we're just going to use an indicator to signal the endpoint. The endpoint is when that indicator changes colors. Which following indicators would you select? Okay, well, first off, we need to remind ourselves when indicators change colors. Indicators change colors at their pKa plus or minus 1. Okay, and if you're listening to this video before we've done the indicator lecture, know that we're going to talk about why. But just realize that indicators are going to change color at their pKa. They themselves are weak acids and bases. So for instance, methyl red's pKa is 5. If I take the negative log of this, I get 5. So its range of color change that's visible to our sight is 4 to 6. This guy is 7 to 9, and this guy is 10 to 12. So the question is, which one is best for this titration? Well, when do we want the color change to happen? Well, we want the color change to happen somewhere in here, right? Because that's our equivalence point. So somewhere in the ballpark of 8 would be great if this would change color then. And which one is best for that? Heck yeah, Crescel red. Crescel red, because the pKa is near, I should say the pKa of the indicator is near the equivalence point, near the pH of equivalence point. All right, the last part. Basically, sketch the titration curve that would result if the weak acid was replaced with a strong acid, such as HCl, of the same molarity. Identify the differences between this titration curve and the curve above. Well, since I know I have a strong base and a strong acid, the first thing that would change about this curve would be the equivalence point. What pH occurs when we titrate a strong situation? We know it's about 7. So if this is where the middle of my sharp rise should be, that means my sharp rise needs to be about that long for this to be the middle at 7, right? And then I'm going to kind of eyeball it. Because it's a strong acid, I know my starting pH is going to be way lower than the weak acid is. So that's got to be like down here. And I also know that there's no buffering region like we have here, so it's going to be pretty much, there's none of this little shoo, it's just going to be bam. And we're going to go flat, 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 and all of a sudden sharp rise and moving on. So review yesterday's video or the video from this morning's lecture. Again, the titration video to talk more about, to hear more about the differences between weak, strong titration curves versus strong titration curves. All right, great. Let's move on to our final problem. A sample of 40 mils of 0.1 molar acetic acid is titrated with 0.15 molar of sodium hydroxide. Ka for acetic acid is 1.8 times 10 to the negative fifth, which was a number we all know and love. Part A says, what volume of sodium hydroxide is used in the titration in order to reach the equivalence point? Okay, so we have to find the volume of sodium hydroxide to reach the equivalence point. Well, I know that at the equivalence point, my moles of acid is equal to my moles of base. I know exactly how much acid I'm using, so because that's what's in the sample. So I'm going to take 0.04 liters times 0.1 of the acid, and that's going to give me 0.004 moles of acetic acid. Again, at the equivalence point, H plus is equal to OH minus moles. So, because I know how many moles of acid, I know that's how many moles of OH minus I need to have. So how do I find how many mils of OH minus? Well, what else do I know about OH minus? I know that OH minus has a molarity that's given to you of 0.150. And that's equal to moles of 0.004 over liters. Hey, that's how I find the liters then. I know that my liters of sodium hydroxide is 0.0267, and my mils are 26.7. Okay, so that's how many mils it takes to get to the equivalence point. Bam. Why do I need that? Well, we'll see, because this is going to build. So the next question says, what is the molar concentration of this C2H3O2 at the equivalence point? So what we're going to have to do here is, remember, this is a titration. So we're adding something strong to something weak. We're adding something strong from the burette into the weak acid beaker. So these are all considered invader problems. At the equivalence point, this is how much base we used, right? We used up all that acid and how much base we used to get to the equivalence point. So what we need to do to figure out what the concentration of anything is, I don't care what we're talking about, we need an invasion equation. Ooh, that rhymes. So I'm invading my acetic acid with my OH minus, and I'm getting H2O, which I don't care about, and C2, I'm sorry, I got to keep consistent, and the acetate ion. All right, so remember, at the equivalence point, what's true? My moles of both of these guys are the same. So that's what's going on in my titration. Zero of this yet. I'm going to lose this. I'm going to lose this. And I'm going to gain this. Okay. Now, how am I going to find? They're looking for this, is what they're looking for. 0.004. They're looking for the acetate concentration. Is that the acetate concentration? No, this is a stoich table, remember? And the stoich table is in moles. So I need to figure out how many liters this whole thing is in. And if you remember, I had the 0.04 liters plus how many liters of hydroxide was it? 0.0267. That's why they wanted us to figure that number out. Okay, this was what was in the beaker or Erlenmeyer. This is what was in the burette that we titrated to. So when we figure this out, the acetate ion concentration is turning out to be 0.05997 moles per liter. All right, we're almost done. Now we just have part C. Part C then asks, what is the pH of the solution at the equivalence point? Well, we just need to finish this problem, okay? This is the invasion. The invasion happened. This is what's left over. So how do we find the pH using what's left over? Well, the war's done. Only AC minus is left. Looks to me like that's a hydrolysis problem. So I'm going to take this. I'm going to make HAC plus OH minus, and I get a 0.0599700 minus X plus X plus X, 0.05997 minus X, X, and X. And I'm going to drop this because this is negligible. But like always, folks, this is a KB situation because KB is equal to the OH minus times the HAC, all divided by the AC minus. So I need to take that Ka of 1 times 10 to the negative 14th, and I'm going to divide it by the Kb of 1.8 times 10 to the negative 5th, and I get x squared over 0.05997. I think that looks good to me. and I'm going to solve for my x, which is equal to the OH concentration, and that turns out to be, oh, I never figured that out. I knew I forgot to do something before I started this video. I'm going to multiply 1.0 times 10 to the negative 14th times 0.05997. I'm going to divide by 1.8 times 10 to the negative 5th. And I'm going to take the square root of that. And I get an X, or an OH concentration, of 9.427 times 10 to the negative 6. I hope this is right because I'm doing it under pressure. And then I'm going to take the negative log of that to get a POH of 5.0256. And then I'm going to subtract from 14, and I get a pH. I'll be reasonable with sig figs here and just say 8.97. Please check my math on that. Even if the math is wrong, the setup is right. So hopefully I didn't mess that up. Anyway, that's it. Thanks a lot. Please review these problems and come see me if you have any questions.